Our last but definitely not least speaker. Ronit Bustin is a researcher in the General Motors R&D Technical Center, and their talk's title is quite simple. It's explaining MCTS. So that's either Milwaukee County Transit System, I googled it, or Monte Carlo Tree Search, but I'm sure Ronit can tell us which is the correct interpretation. Thank you, Ronit, for coming here, and enjoy.
Thank you, Ray. Of course. Thank you, everyone. Very excited. I'm guessing this is how I point, and this is, yeah, okay, great. Thank you. Very excited to be here and share our work with you. This is joint work with my collaborator, Claudia Goldman. So I'll start with motivating what we did. So our domain is autonomous vehicles, sequential decision-making for planning systems for these vehicles. And our goal is to explain first to the passenger, but also even to the engineer, the decisions of the algorithm. And the scope that we looked at as we were given a specific algorithm from the family of alpha 0, for which there's the vehicle observes a state at every time. This, for example, could be the speed, the lane location, relative location in the lane, speeds and relative orientations of the surrounding vehicles. It could be additional map information and more. And for each state that the vehicle observes or the planning system observes, it has to perform a decision. And it makes use of a computational budget that it has because of the complexity of the problem. It takes that state and it constructs a Monte Carlo tree search. It gradually constructs that tree. It starts with a simple S0, that's the current state that we observe, and it gradually expands that tree, okay, for using that computational time to reach the best decision that it can. And eventually it gets a tree, a complete tree. This is a very small example of such a tree because in reality, due to the complexity of the problem, due to the number of actions, etc., the trees can be very, very big. And according to that tree, looking at the decision or the possible actions that were considered from the root, the algorithm decides on the best action. It could be usually according to the maximum number of visits. So in this case, it would probably be the green action because the subtree below it is bigger. So that will be the action that will be performed. The action will be performed by the vehicle. And again, the same procedure. It will be for the next state, according to the way the vehicle advanced in reality, we'll construct another tree, and so on and so forth. Okay? And our claim is basically that we come from the world of explainability. We want to explain the decisions that were made to the passengers, to the engineering team. Our claim is that a lot of the reasoning of the algorithm is encapsulated or summarized within this Monte Carlo tree, or the sequence of Monte Carlo trees. These huge trees contain the reasoning, and in order to explain, we need to extract information from these trees. Okay, regardless, there's other aspects that can be explained. There's a neural net, there's all kinds, but a lot of it is summarized already in the tree. Okay, so our goal is very basic in some sense. We have that tree, we want to extract information from it for the purpose of explainability. So we looked at this at 2 stages. The first stage was, the difference between the 2 stages was the first that was kind of a sandbox case that was, the action space was limited. It was a discrete action space, 7 possible actions, limited actions. We had acceleration, harsh acceleration, deceleration, a bit going right, going left, 7 possible actions. All of them had semantic meaning. And semantics is very meaningful and very important for us, coming to explain this to the users. So in this case, in the original case, the discrete action space, we had semantics. The realistic case is continuous actions. There are trajectories in space. There, the main issue is that we lack semantics. Another issue is that two actions could be very similar. They could look very, very similar in space. In both cases, the trees can be very, very big, and our original problem already in the case of the discrete is to extract information. And what I want to explain now is basically, or convince you that the reasoning is there, and the question is, in what sense is the reasoning, and what information can we extract? So for that, I'm going to come in a nutshell repeat what MCTS does in very quickly, just to motivate our approach. So MCTS, in a nutshell, constructs gradually the tree. So it starts from the root, and at every iteration, it adds another node, or usually it adds another node. And it does so by repeating 4 steps, okay, iteratively repeating 4 steps. Starting from the root of the node, the root of the tree, it goes down through a selection process, basically going down the tree in a specific path, reaching a node that was not fully expanded. It then expands that node, meaning it adds in a semantic, it adds a node or adds an action. And in that sense, it needs to provide information for that node, which it does either by going to the neural network, asking what is the value or the accumulated value of that, or estimated value of that node, what are the priors from that node, or does a Monte Carlo simulation, hence the name. Given that it has that information, now it backpropagates that information up the tree, updating the path and the values throughout the tree, going back to the root of the, and again, iteratively doing that over and over again, according to the computational budget that we have, thus expanding the tree to a full tree. And the main aspect here, or the main issue that I want to emphasize, is that the construction is not arbitrary. We haven't arbitrarily created a tree of future possibilities. We constructed it in a very specific way, following the UCT, the upper confidence bound, meaning that we kind of pushed towards locations that had either high value, okay, nodes that had high value, or in a case that they didn't. Okay, so in the examples that we saw here, for example, we can see that in this case we have a single child. That means that we didn't go, we saw that there's a high value here, but this node has a lot of children, so it expanded differently. So in some sense, what we're trying to capture is the structure of the tree. The structure of the tree tells us where information lied. Where was it? We'll go here. And that information we can see it, we can view it, right? When we depict the tree, we can view that structure, but we want actual values, numbers that will tell us what was the structure of the tree. And for that, we use entropy. We use the measure of entropy, and we can calculate, so entropy of the random process that is defined by the edges at each level. So these would be the edges here coming from the root. That would be the random variable x0. x1 would be the values of these edges in the second layer, and so on. And for each node here, we can calculate a value, which would be the entropy of the process of that subtree. The entropy of the process of that subtree, and it will correspond to the structure of that subtree. And given that, that will give us information about where the reasoning of the algorithm, where did it search more, okay? And what I'm trying to, the two issues that come to consider here is, can we efficiently compute it? Well, can we compute it, and can we do it efficiently? And how can we use it? So the computation can be done very easily, so we can just expand the entropy of the process, and we have a recursive equation to perform. So if you give me a tree, and I go down the tree recursively and follow this equation, I will be able to compute this for every node along the tree. So every node will have the value of the entropy, which will correspond to the structure of that subtree. Moreover, we can actually compute it while we construct the tree during the MCTS process by piggybacking the backpropagation process. So whenever we did the backpropagation from a node up to the root, we can actually update the values of the entropy. So once we have that completed tree, we will also have the entropy values at each node. That gives us another advantage, not only the efficiency, since we haven't added complexity to the calculation of the Monte Carlo tree search, but we also have the entropy anytime. So at any time during the process or the construction, we have the entropy. So that brings us to the usages of this. The usage, first of all, for XAI, so we can use the entropy measures for explainability. We can say, for example, explanations that will rely on that. We'll say the algorithm was more confident in its specific choice than the alternative choices, okay? It was more slim in its structure, or it was, it considered, there are many possibilities if we follow this specific action, or we can use it not directly, not in the content of the explanation, but actually in the timing of the explanation. We can say we're going to explain or provide an explanation only under specific values for the entropy. Only if the entropy was above or above some value, we're going to provide an explanation, which is also a critical question when it comes to explainability. Other usages are, of course, first of all, we can influence the MCTS construction. Because we have these values anytime, we can use those to influence. And finally, something that we did implement, and I'll just show you the next slide, is using it for reduction. As I said, the trees themselves can become very, very big. And it's also for purposes of storage or communication, but also for purposes of explainability. If we want to compare the current tree to previous trees for purpose of explainability, we sometimes want to reduce them. And we use the entropy value for a trade-off between size and entropy. So we got trees that were reduced in this way. So this tree was reduced this way, this one reduced this way. The trade-off basically says reduces as much as possible, but keep those interesting parts of the tree there. So basically we get a reduction that is following this trade-off. So I know my time is up. I didn't go into trajectory. I'm just going to say that the lack of semantics is something that we also tackled. We used clustering as a method down the tree. And the main issue with clustering is the fact that we need to consider how, according to what information to cluster. But I won't go into this because kind of time is up. So thank you for your attention, and ready to get questions if you have any.
Thank you. Guys, we have time for exactly one question. Okay, I didn't mean to get you so scared. Please.
Get a rough idea, how big are them to the user and how are they likely to have it?
The trees themselves are not the result that we present to the users. They're just a tool. We're extracting the information at this stage. What I've shown is extracting or computing the entropy information throughout the tree as a tool for constructing the explanation. So as I said, once you constructed it, you can use it to determine, for example, when to provide an explanation. Say that only when the reasoning of the tree was confident enough, the entropy was high and was low enough, you will give an explanation. Or you can give an explanation that say the action that was chosen was opened more, examined more future possibilities than the alternatives, something like that. So it's a tool, basically. But the trees, in general, can become very, very big. These are from the discrete action space, but in general, there could be hundreds of actions, and the size of the tree is basically limited by your computation times. Yeah.
Thank you again. Okay, so thank you. I think this has really reinforced my belief that reinforcement learning is moving forward, and both in regards to the theory and in regards to the practice, and the exciting applications are cropping up around us. Please help our speakers learn how well they performed by reinforcing them with a big round of applause. Thank you.